used in practice for classification kind of looks like this. Right? So it doesn't matter too much which one you choose. Right? They all kind of look the same. Right? Yeah?
So it seems like all these measures will do really well when you just give each data point its own box.
So, I'm sorry?
If you just give each data point its own box, then they'll all have really good impurity measures because it's kind of like, it seems like you could easily map. How do you like regularize away from like just overfitting and having each data point have its own?
Oh, in the extreme case where each leaf node contains exactly one data point.
Yeah, because then you're going to do great for impurity, right?
Right. Yep. I will get to I'll get to against controlling against overfitting in a few slides. Yeah. But you're right. Decision trees have the ability to learn. I mean, in the limit of infinite infinite depth, they have the ability to learn arbitrary functions.
Yeah.
Near arbitrary functions, right? Okay, so this is the top-down training algorithm that's used for training decision trees with, including both the query, the choice of query at each internal node, and also the structure of the tree. So the basic idea is as follows. We start with the root node, we loop, and we pick we start with just the root node. We pick the root node, we loop through the all possible splits and choose the split that has the greatest impurity reduction, creates a reduction in impurity, and then repeat over all the leaf nodes until some stopping condition is met that guards against overfitting. So step one, we have just the root node. All the training data belongs to the root node. This is the impurity measure. We consider this split. Sorry. We consider this split, which is we can split on either age and all thresholds for age, and male and all thresholds for male. And then we find the one that has the maximum impurity reduction. So this has the sum of these two has the maximum impurity reduction over this. Then loop over all the leaf nodes again. So loop over this leaf node. Try all possible splits of the training data that partitions to this leaf node. Loop over this leaf node and try all possible partitionings of the training data, queries of the training data that partitions into this leaf node, and then choose the one of all possible queries that split this leaf node and all possible queries that split this leaf node. Choose the single one that maximally reduces the impurity, and then we keep doing this until we reach some determination criteria. And in general, the decision trees need not be balanced like this. This is just for simplicity of demonstration. So we can go like this, go like this. Do the other dimension. Took me a while to make these slides. Okay, then we decided this has the best impurity reduction after we looped through all possible partitionings over all possible single dimensions. We decided this has the best possible impurity reduction. Then we loop over the first subtree. Loop over the second subtree, all both dimensions. You might wonder what a professor spends his time doing. Okay, so then we decide, okay, this is the split over both subtrees, over all possible queries over both subtrees. This is the split that gives the maximum impurity reduction. And then we do it again, again, until we've met some termination condition, and we stop. So this is top-down training. So what are some properties of top-down training? Well, every intermediate step of top-down training is a decision tree, because all top-down training does is take a leaf node of your intermediate decision tree and split it into two leaf nodes. That's all it does, right? So you could stop at any time you want and have a decision tree. It's a greedy algorithm. What that means is it doesn't backtrack. So if you made a split, you cannot choose another split at this level. You can only make refinements of this split. Yeah?
So why didn't you search both subtrees for the next split before why can't you just search the first side and find the right one and then search the other side?
So in practice, usually people do that. I'm just sort of, right, so in practice, I mean, that's what people do. And the reason why, okay, because it's a greedy algorithm, at every iteration it wants to choose the split that maximally it reduces the impurity over the entire tree. You can absolutely memorize your previous results. Like, there's no reason why you have to like recompute the splits over and over again. Right? As long as you memorize them, you have like a priority queue of possible splits, right? If you think about data structures, you have a priority queue of possible splits. You just have it sorted by the impurity reduction. And you just pop off the top, right? And you can add to it. So there's no need to recompute. But and in practice, you may decide that I should just commit to this one no matter what, right? It's just for simplicity. Like when some people try to theoretically analyze decision trees, and then when you do so, you have to do it in a serial way. What you're talking basically is a parallelization, right? Just sort of commit to these two simultaneously, effectively, right? And when people sort of try to analyze decision trees theoretically, they need to analyze a serial algorithm. Yeah.
So is optimizing for impurity at each level the same as optimizing impurity at the end?
It's greedy optimizing for impurity at each level. Right, given that this is my fixed structure of the tree, and the only thing I can do is make a refinement of the tree, then that's the best. Then I'm maximally optimizing that one-step refinement. Right. So given I'm not allowed to backtrack, and I'm not allowed to look far into the future, it's optimizing a one-step refinement. So the optimal decision tree, in the worst case, is somehow you have to try all possible combinations. It takes exponential time, right? Because you do all possible backtrackings. Yeah.
It's a Kobe algorithm, so the final result you get will possibly not be the optimal one, right?
That is right. It is almost certainly not the optimal one. In terms of the optimal in terms of the size of the tree. Optimal requires an optimality condition. What is the smallest tree that gives this accuracy, right? And a top-down induction almost certainly would not give you that, right?
So there is no trade-off that says that this one is the smallest size of this accuracy. You will just try, right?
It is. I forget the exact complexity class. Finding the optimal tree is. It's PPAD. Okay, it takes exponential time to find the smallest possible tree with a certain accuracy level. Right. So that's why people do top-down greedy induction. Okay, so that's the question. Even though it's not the smallest possible tree, right? If you train if you build a top-down induction, long enough, you can perfectly fit the training data. You can perfectly overfit to the training data, right? So one question in the top-down induction algorithm is stop when you meet some termination criteria. And now we're going to talk about what that is. Right. So here's a thought experiment. Suppose we have sort of these two. Suppose we have this split, and then this is a refinement of this tree. So this is an intermediate version of this tree, right? And obviously this one has lower training error, right? Which one has better test error? If in the limit, if we kept refining this tree, we can get 0. Or actually, this one is perfectly refined. It has 0 training error. We don't actually want to commit to this tree. Somehow we're just overfitting like crazy to a finite training set. And this is basically the stopping condition you could think of as somehow an equivalent notion of regularization in the analogous to the linear model case. So here's a number of stopping conditions. Obviously, you can use a held-out validation set and stop when the validation error no longer goes down. So that's early stopping, right? And that you can always do. I'm going to talk about some other stop conditions that more closely mimic regularization. One is minimum size. Do not split a leaf node if the resulting children leaf nodes have training data size smaller than some minimum size. So each leaf node needs to correspond to at least 10 training examples. Otherwise, we're not allowed to split. And in my experience, this is the most common, most popular stopping condition. Maximum depth. Do not split if the resulting children are beyond some maximum depth of the tree. maximum number of nodes, that's still the number of, this tree already has a maximum number of valid nodes. Minimum reduction in impurity. Do not split if the resulting children do not reduce the impurity by some threshold, like 1%, 2%. So these are all valid. Yeah?
The minimum size is, you take that minimum size and like, it depends on the size of your training set, or how do you choose the size? Take it as a fraction of the training?
You know, this, if you think about it, a minimum size is sort of, these are sort of minimum size 10. All trees with minimum leaf node size 10 is a subset of all possible trees with minimum leaf node size 5. Is a superset of all possible trees with minimum leaf node size 30. So they're like sort of you know, sets of model classes, and you could do cross-validation to pick the one that gives you the best error.
Is there a rule of thumb for picking the size?
No. I hesitate to say a rule of thumb. I mean, I have a few numbers I always try first, but you know, I've been shocked at what the optimal minimum leaf node size is for different prediction problems. Yeah.
So how do you decide, like, is it minimum size just for the best split? Like, what if the second best split is not breaking the threshold, but the best split is making the threshold?
Right. So typically, if the best split makes the threshold, you just basically discard all splits that violate the minimum size criterion, and then choose the best split remaining if there exists one. Otherwise, you stop. And you know, if you do the homework and use scikit-learn, this is some flag you can set as a stopping condition, I believe. And you know, if you're interested in pseudocode, this is just sort of a pseudocode description of what I just described. You loop through every leaf node, you loop through every query in your query set, you try to, you know, you check that the minimum leaf node size is valid. If so, you add it to this set of queries, of feasible queries. You choose the query within the feasible queries that has a minimum reduction in loss or impurity, maximum reduction in impurity, and then you rinse and repeat. Okay, so classification trees is what we talked about. Regression trees are a little bit easier to think about. So in classification, their labels in this case are 0, 1. They can also be -1, 1, doesn't matter. In regression, labels are real value. In classification, you predict the majority class. In regression, you predict the mean because you're trying to minimize the square root loss of the leaf nodes. They're both piecewise constant. The goal is to minimize 0, 1 loss based on some surrogate. In regression, the goal is to minimize squared loss, and you could just directly use squared loss because it's continuous as the impurity measure. It's just a recap of decision tree training, top down, greedy, minimize some impurity, which corresponds to some surrogate training loss, until some stopping condition, conceptually equivalent to regularization, or analogous to regularization, and finding the optimal trees and track. Recap of decision trees. Piecewise constant model class, highly nonlinear. Induces axiom on partition of the feature space because the dominant mode of decision tree training is to use single feature binary queries. You try to minimize the purity of the training data and the leaf partitions, and often more accurate than linear models, provided you have enough training data. Okay, any questions about basic decision trees?
So,
Yeah, sorry about that.
for regression trees, so is there anything different? I mean,
Nothing's different.
getting a continuous variable, you just
The only
add it.
thing that's different is your purity measure is squared loss.
So how do you compute the final leaf? You just add the continuous values that you get at each interior node?
You add the. I'm sorry. I'm not
So
sure.
how, you just take the average of all
You
the
just take what's in the leaf node. Like you just take the mean of the labels in the leaf node. Like just like in classification, you take the majority class in the leaf node. In regression, you take the mean value of the leaf nodes, of the labels in the leaf node. Because that if you can't split anymore, the best prediction you can make for that leaf node is the average, because that minimizes the squared loss of that leaf node. Sorry, question?
How do you exactly search for the best partition?
You do a for loop.
No, but I mean, there could be infinite.
Given finite training set, it's only finite.
Sure, but I can say I have vertical line x equal to something.
Yeah.
I can have if it's a continuous real line, I can pick any particular partition.
But if you have a finite training set, most of those are going to only a finite number of those. All right, there's a finite number of equivalence classes, right?
Right.
So you just pick those, or you pick one in the middle of two training examples, or you just pick some percentiles. You don't have to loop through all of them. Okay, so now let's talk about bagging. So bagging is focused on optimizing the bias variance trade-off. In the literature, typically of decision trees, although you could use other base model classes as well, right? So bagging is a method for minimizing the variance of the bias variance trade-off without compromising on bias, and it's not specific to decision trees. And then we'll close with a brief discussion about random forest, which is an extension of bagging that is specific to decision trees. Sorry, did you have a question?
Oh, no, I looked back in it. Or I was just wondering for the minimum size, it was the number of things inside that size.
Yeah. Okay, so this is just a recap of things you've seen already. So imagine that we have some true distribution of data points unknown to us, and our goal is to train a model on a finite sample from this true distribution that has low error, right? And our goal ultimately is to have a model that has low test error, which is if you take the distribution of data points on the test distribution, the expected test error should be low. Right? And overfitting is the case when test error is much higher than training error. So this guy is much higher than error induced by averaging over the finite training set. Right. Okay. So imagine this is the true test distribution. This is our finite training set sampled, from this distribution, and we train a model that that gets these correct and these incorrect, and we want to ask, what is the test error of this model, right? So the bias variance composition, and again, I'm only showing it for squared loss, so for the regression case, because it's mathematically sort of convenient. The bias variance composition of squared loss, so this loss term is now squared loss, so the squared value of 1 y minus h of x. So the expected squared loss decomposes into a variance term and a bias term, where the bias term is the average prediction over the randomness of your training examples. So given a new set of training examples, I would train a new tree, and if I were somehow able to at least conceptually repeat this process, this would be the average predictor. This is the bias term of my model class, and this is the variance term, the variability of that prediction of any individual predictor from the average predictor. And you've seen this already, go for linear, quadratic, for cubic, and the bias variance trade-off looks like this. So the black line denotes the average model from a small subset of training examples chosen from this distribution, if you were to repeat that process, and the green line corresponds to the variability. And so the goal, and so if you just were choosing between these model classes, you would choose the quadratic because it minimizes the bias variance trade-off in this particular case. Overfitting, high variance in a model class, so the model class has high variability depending on the specific training example set you sample from the training set, implies overfitting, which means the model class is unstable to the choice of training examples. The variance increases with the model complexity, so decision trees can have a very high variance. Variance reduces with more training data. So as you sample more training examples from the test distribution, the variance in the model class decreases, becomes more stable. In the limit where you have an infinite amount of training data that perfectly represent the test distribution, you have zero variance. You always get the mean and all of that. High bias implies underfitting. Even with no variance, the model class has high error. Bias decreases with model complexity is more or less independent of training data size for most model classes. So this is the example of a tree that we trained on a finite training set. Now, the question is, how well does this sort of actually do on the test distribution, which has many more data points, right? And we may find that we regret it, if we knew what the test distribution was, or had more samples from this test distribution, we may regret some of our previous decisions. Right? So, decision trees are super low bias, super high variance models, unless you regularize a lot. If you regularize a lot, though, they're often worse than linear models, because each partition is partitions on each leaf node, each internal, partitions on a single feature at a time. Therefore, if your decision tree is super small, it actually can be much worse than a linear model, which can partition on every feature simultaneously. So different training examples can lead to very different trees. So here's where bagging sort of comes into play. The goal of bagging is to reduce variance, right? So here is sort of a simplified formula, the bias variance trade-off. In the ideal setting, suppose we were able to draw many training sets S prime from the test distribution, right? So we train a model using each S prime, and then we average the predictions. So just it's a little bit sort of weird to think about this, but just imagine we could do that. Imagine that we were able to just pick a training set of size 5,000 examples, train a decision tree, get another training set of 5,000 examples, train a decision tree, repeat this process a number of times, and then predict the average of all the trees as our final predictor. Right? So we just sample this S prime independently multiple times. So what does that mean? Well, because the S prime is sampled independently, the variance here reduces linearly, and the bias is unchanged. Right? If we're able to do this process. Of course, in practice, this is preposterous. Like we can't do this. And we just have one single training set. That's it. And so what we do in practice is instead of sampling S prime from the test distribution all over again, which we can't do, we resample S prime from the training set S with replacement. And then given each such resampling of S with replacement, we train a model on this S prime, and then we average predictions. So we have a test distribution, we have a single training set, we generate S prime, which is a resampled training set from S with replacement, sampled with replacement. And so of course, the variance will not reduce linearly in this equation because the S primes are correlated. And if you do this, the bias often increases slightly, but it's not too bad. And the process of sampling with replacement from a finite training set to generate a new training set is called bootstrapping. And so bagging is shorthand for bootstrap aggregation. Any questions about bagging, the concept? So here's how it works. Here's how it basically works. It's very simple. We're given a training set. We generate many bootstrap samples from S prime from this training set. Right? These are samples with replacement from S. The size of S prime is equal to the size of S. There's often duplicates of S in S prime because it's sampled with replacement. And then we train a relatively minimally regularized decision tree in S prime, so it has high variance, low bias. And then we average. That's bagging. That's bag decision trees, or bagging for decision trees. You might ask, could this possibly work? Right? Yeah.
What does it mean to average a decision tree?
So let's say I have 100 trees, and 85 of them predict, for a single example, 85 of them predict 1, and 50 of them predict 0. For classification, I predict 1. Right? For regression, it's literally the mean. Right? For classification, it's like the majority vote. Yeah.
What's the difference between bagging and cross-validation?
Cross-validation is a method for selecting a model class. And bagging is a method of aggregating multiple decision trees. So you can think of bagging as a new model class that is the average over many decision trees. Right? So cross-validation is a method.
What's the difference is that instead of picking the best tree, you're averaging all of them. Right? Maybe cross-validation, we have all those trees, we pick the best one, here we only average them. Right?
Not only that, in cross-validation, you don't do bootstrapping. In cross-validation, you have your splits, and your goal is to choose the best model class. Here, you're doing bootstrapping. So the idea of bootstrapping, the idea of bootstrapping is that the idea of bagging is to optimize this bias variance trade-off, right? Yeah, if only we had multiple independent samples of our training set, then we could train multiple instances of our model that, you know, the bias stays more or less constant of each model in the model class if you average them, but the variance decreases, right, if we average them, right? This is a standard statistics, right? And so it's a way of building a new model class, a meta model class from an existing model class that has a better bias variance trade-off than the base model class. Cross-validation is an evaluation methodology designed to help you select the best model class. This bagging introduces a new model class. So they're used for separate purposes. Yeah?
I don't understand what do we find a new model is still a decision tree, right?
It's the average over many decision trees. Okay, I see. You can still think, I see, okay. So you can still think of the average over many decision trees as being representable by a decision tree, right? So you could argue that maybe there's a there's an equivalence between them, and that might be true. But it may be hard to train a single decision tree. Okay, so the answer to your question is a little subtle. No. Okay, I think I can, I'm not sure, but I think I can construct an example of the average of a few decision trees that is not efficiently representable by a single decision tree. Right? The bagging is the average over multiple decision trees. So it's a meta model class. Yeah.
So I'm still a bit confused about the averaging. So say one of my samples, my tree converges after one sample, I just get just two leads. And another one, I get 100 leads. I'm not understanding how I average those together. Like what it means to average those together.
You average the predictions.
So you're keeping track of all you're not coming with one tree, you're keeping a family of trees.
The trees are not aggregated together. The trees are kept separate. So the bagging can be applied to any model class. Yeah, you only average the predictions. So if you have 100 trees, you just run your prediction algorithm on all 100 trees. You take the predictions and you take a majority vote of the predictions as your final prediction for classification. For regression, you run your regression trees, you classify all 100 trees, and you take the mean. Do you have another question?
So the cardinality of the sample, bootstrap sample set, should it be always set to be the same?
In the standard bagging approach, it's set to be the same.
Oh.
The reason is because you want to keep if you have a smaller data, so remember, okay, so this is specific to this is more important for decision trees, but also applies to other model classes as well. The complexity of your model class grows with the number of data points you have, right? If you have a lot of data points, you can regularize less for linear models. If you have a lot of data points, you have a deeper tree, right, for decision trees. So this is important because you want this bias term to be relatively to not change too much, and you want to optimize the variance. You can't do that if the training sets are really small, right? Because the trees will have high bias because they're going to be simple trees. Yeah. Do you have yeah.
So you get a bunch of trees using this bagging. Do they all come with the same weight, or is there a reasonable way of giving more importance to some of them?
To some of the trees? Yeah. We will look at a version of this. We will look at an algorithm called boosting that does weight the the learn trees differently when it averages them. But bagging, it's uniform weight.
So this will kind of work on everything, on any kind of model class as long as evaluation is cheap, right? As long as it's easy to just, you know.
Well, I mean, it'll work even if evaluation is
practical.
expensive.
Yeah, it's practical.
sure, yeah. The reason why it works, the reason why it can give you a performance gain is that you have a model class with low bias, and you don't care, you deal with overfitting by just reducing the variance. And obviously this is not perfect because you're doing a sort of an indirect sampling of B of the test distribution, but it can often help. Yeah.
I just wondered, if you introduce weighting, wouldn't that also again like promote overfitting? Because it then turns into like.
That's a great point. And when we talk about boosting in the lecture on Thursday, we'll see how they deal with that.
Okay.
Yeah. So just a teaser. So boosting says, okay, I'm going to make the variance small, and I'm going to optimize the bias. Right. So what does that mean? That means a very simple tree. Very simple tree has very low variance, right? And then I'm just going to average a bunch of simple trees together to minimize the bias. So I'll get to that. So bagging says I want to keep the bias relatively constant and minimize the variance. Boosting will keep the variance relatively constant or small for simple model classes and minimize the bias. Right? And so we'll talk about it on Thursday. Yeah, so when I say average, I mean average of their predictions. Yeah?
So is this equivalent to like if we put some repeated points and then keep the size of the tree unchanged, and we can get the same?
You have to retrain the tree on the new data set.
Yeah, I mean, but like the new data sets are actually, you put this sum of this.
Oh, you're saying instead of creating new data points, you just say this data point appears twice?
Yeah.
Yeah, that's equivalent. Yeah. And in fact, that's what they do in practice. They don't actually create a new data point. Yeah. Like if you look at implementations of bagging, they don't actually. Because in practice they're equivalent, and it's just a waste of space.
So this bootstrapping procedure, you do not actually introduce new data points into your training set.
No,
So
I mean
there's
nothing,
no
unless you actually go out
addition.
and collect training points, nothing can introduce new training points.
So there's basically, can I say that there's no addition of new information to your training set? And it's sort of like an intuitive way to think about this, why this procedure works if you do not.
Okay, I'll get to that in a couple slides. One question is, does this even work at all? Right? It's like, when I first learned about bagging, I was like, there's no way, this is like black magic, right? There's no way this can possibly work. And surprisingly enough, it actually works. It doesn't always work, of course. There are certain cases where it doesn't give you much. But here's one example where it actually works really well. And if you're interested in a really detailed paper exploring bagging and boosting, which I'll talk about on Thursday, here's the paper. So here is the tree, decision tree, 3 different bag versions. I won't go into the details. It's decomposed into the bias component of the loss and the variance. And you can see bagging, the bias term is more or less the same. The variance term drops significantly.